Welcome back, welcome back. Time for Chapter 10, Challenge Problems. We're starting with 10.95. This is an A, B, and C problem. So I'm going to go through each letter as they come along. My apologies for waiting like 3 days to make these videos, or the next video. My life's been pretty hectic the last 2 days. If you couldn't tell, we're at a new location. This is not my apartment. We're at my dad's house now. Which is one of the reasons that I haven't been making videos, because I had to go buy a new board. And as you can tell, I cut this one in half much better than the other one. In fact, I might bring this back to me with my apartment and replace the new crappy duct tape board. Maybe a good idea. Alright, so for this, we're asked to write the formula for the conjugate base of H2S and then H3PO4. So, this was covered in the other video. If you're asked to write the conjugate base of something, you're going to want to remove an H, because the base is what accepts the H. So these are currently acids, because they're going to be giving away H's. So the base for this would be, since we're going to move one H, it would be HS. We've taken one away. And it'll be HS negative, because when you move a proton, the charge goes down by 1. Now we have H3PO4, which gets turned into H2PO4. And what would be the charge be on this? Since it's neutral here, it'd go down to a -1, so negative. That's that. That's relatively easy stuff, right? Of course it is. And if not, you can always text me. What is the Ka expression? Okay, so for, I guess, acids and bases, the Ka, this is kind of like Kc, except it's with acids and bases. So whenever you're not given the formula, you're going to want to assume that it's in water. So this is our chemical equation here. We have H2S. You're going to want to assume it's in water, so it'll be plus H2O. And then it'll be H3O plus. And then, let's see here. Give me 1 second. And then HS negative. Okay, so let's plug this in for the Ka. These are our products. These are our reactants. So Ka equals H3O plus HS negative over H2S and H2O. Looks like H26. H2O. There we go. And that's your Ka. There you go. Very simple stuff. These challenge problems aren't exactly all that hard yet. We'll get to that, don't worry. Next up it asks, what is the weaker acid? For this one, since we don't have any numbers, we can't really do anything. If we plugged in the numbers for the Ka and got like something times 10 to the -7th, then that would be a pH of 7, because you always use this. It's like the logarithm thing. He explained this in class. Logarithms basically, I'll just say it up. This would be turned into 7. If it was 10 to the -10th, it would be a pH of 10. If it was 10 to the -1, it would be a pH of 1, which is a very, very acidic thing. This is decently basic, and 7 is neutral. So if it's higher than 7, it's basic, and if it's lower than 7, it's acidic. 7 is neutral. But on this question, since we're not given numbers, we can't really do that. So there's a chart in the book. I think it's 10.13, I think it is. Go check on that. That'll tell you what the stronger acid or the base is. But that won't be asked without giving us numbers. Alright, let's do 10.96. Exact same thing, except with HCO3, just to rerun it again. HCO3 and here we go. And then HC2H3. Whoops. Yes, neutral. Yes. Alright, so let's draw the conjugate base. So we're going to remove an H, so it would be CO3 2 minus. And then I'm going to move the H here, be C2H3O2 negative. No problem. What is the Ka expression? Let's do it for HC2H3O2. So let's do it for that. I don't want to do it for both because you already will understand that. So it'd be a HC2H3O2 plus H2O yields H3O plus gain a proton. And then the base, the conjugate base of the H, C2, just C2H3O2 minus. Alright, so let's plug in our numbers, or plug in the letters for Ka, and we get H3O plus over C2H3O2 minus over, now we're doing over, H2O, and then C2H3, blah, 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 blah. That's that. No problem. And to answer part C, you got to look at that 10.13 picture thing. It's a chart in the book. It'll tell you what acid is stronger. Next up, we have, here's a fun one. Okay, so a solution of 0.205 moles of NaOH is used to neutralize 20 milliliters of an H2SO4 solution. This is 97, by the way. If 45.6 milliliters of the NaOH is required to reach the endpoint, what is the molarity of the H2SO4 solution? Alright, here we go. So remember a long time ago, I think it was like chapter 7 or 6 or something, you had to follow that set of patterns with the mole-to-mole conversion like you do grams to moles, moles to moles, moles to grams, or molecular weight to grams, blah, blah, blah. Well, hopefully they do. Because this is just like that, except it's different steps, but you basically memorize a set of steps and can use them over and over again. So it's not insanely hard, it's just memorizing the steps. So let's plug in what we have. We have 45.6 milliliters of whatever, and we'll start with that. I think that'd be a good place to start. Yes, it would. So first let's draw our chemical equation. That would be a better place to start. Plus 2 NaOH. One sec, I'll move out of the way so we can see the problem. H equals Na plus H2O. This is liquid, these are aqueous, just FYI. Alright, so let's start with what we're given, and that's 45.6 milliliters of whatever. So here we go. 45.6 milliliters of, what is that? NaOH? Yes, it is. So now we need to convert these milliliters into liters because we're going to be using molarity a lot in this. Molarity is moles per liter, FYI. That's the definition of molarity, is moles per liter, so know that. So we're going to convert that to liters. So it'd be 1,000 milliliters on bottom, right? To let the milliliters cancel. Milliliters. Next up, we're going to use our liters and then the provided moles of NaOH. So be 1 liter on the bottom, and then 0.205 moles, because that's what we're given. Ugh. I got space here. Moles of NaOH. Next up, we're going to use the mole-to-mole conversion that we're given in this. So it would be, let's see here, it would be 2 moles of NaOH. Yeah. 2 NaOH. And then it would be 1 mole of H2SO4. Yeah, because those are what's reacting. So 1 mole of H2SO4. And that, let's do the math for that. Give me 1 second here. It'd be .00467. Yeah, moles of H2SO4. Alright, so we have that. And so we're trying to figure out the concentration of, or the molarity, sorry, of the H2SO4. So now we have moles of H2SO4. So on our molarity definition, great. So molarity equals moles over liter, right there. So we have our moles, so it's 0.00467 moles of H2SO4. Now it's time to figure out our liters of H2SO4. So we're given it says we have 20 milliliters of H2SO4, right? Let's see here, yes it does. So 20 milliliters of H2SO4. How do we get these milliliters converted into liters? Well, this is a really, really easy one. It'd be 1,000 milliliters on bottom, and then 1 liter on top. So just divide that by 1,000 and you get 0.02. 0.02 liters of H2SO4. So let's plug that in. That's liters, by the way. Liters. And these are both of H2SO4. So now let's do the math for that. 0.00467 divided by 0.02. Oops, messed something up. 0.00467 divided by 0.02 gives 0.223. 0.2335. So this right here equals 0.2335, and that's our molarity of H2SO4. And that's what it's asking for. So yes, I think it'd be 0.234 because you're going to significantly figure it out to be 3. It's either one or the other. I'll check later. Anyway, there's your answer. So thank you for watching. I'll get back to making more later. Have a very great Thanksgiving and eat till you get diabetes. That's what I always say.